Alright, in this lesson I'll be going over section 4.4, which is the fundamental theorem of calculus, along with some other ideas. But the fundamental theorem of calculus is pretty much the simple way of determining the definite integral. So you don't have to work with all those Riemann sums and the limit process and all that. The definition is, if a function f is continuous on the closed interval ab, and capital F is the antiderivative of the function on the interval, then the integral from a to b of f of x will just equal the antiderivative when you plug b into that minus the antiderivative when you plug a into it. So I'm just going to jump into some examples. It'll catch on pretty quickly because it's such a simple process. So this first one, we want to determine the definite integral from 1 to 2 of x squared minus 3. First thing is notation. So with fundamental theorem of calculus, usually you'll see it'll be like this, and then you'll have your antiderivative in here with a and b right there. It may also just be antiderivative, and then they might just have like just one side. But these two just indicate fundamental theorem of calculus. So first thing you want to do is just find the antiderivative of your function. So you're going to, if you can recall from 4.1, you're going to raise your exponent by 1 on the variable, divide by new exponent, and then for the 3 it's just going to be 3x to the first, so 3x divided by 1 is just 3x. And then we're going to put in our notation for fundamental theorem of calculus. In this case our a is 1, so we're going to put it right there, and our b is 2. From here what you're going to do is just plug 2 into this, and then plug 1 and subtract the 2. So it'll be 2 to the third divided by 3 minus 3 times 2. So that's what it comes out to be when you just plug the 2 into this equation, minus 1 to the third over 3 minus 3 times 1. Do a little bit of simplification, and you get 8/3 minus 6 minus 1/3 minus 3. And after you do all of the common denominators and everything, your integral comes out to be negative 2/3. Second example is going to deal with an absolute value one. So recall that absolute values, they're going to be a little bit more tricky, but it wants from 0 to 2, so 0 to 2. So what we'll be finding is this area plus that area. First thing we need to do with absolute value is, say we weren't given the graph and we didn't have access to a graphing calculator, we would need to find out just where the absolute value graph hits its point. So to do that, we'll just set our whatever's inside the absolute value equal to 0. Solve for x, and you get x equals 1/2. Now we need to figure out, okay, from 0 to 1/2 and from 1/2 to 2, which one will give us a negative value and which one would give us a positive value if we plugged it into this 2x minus 1. So say we plugged in, say we plugged in 0.25 into this equation. 2 times 0.25 minus 1, that's going to equal negative 0.5, which means that that's going to be a negative from the interval 0 to 1/2. Let's try plugging in a 1. So 2 times 1 minus 1, that equals 2 minus 1, which is just 1. That's a positive. So that means what we're going to now do is just split it up, split this. Now that we have this information, we can split this up into two integrals. So we can have from 0 to 1/2 of negative 2x minus 1 dx, since we found right here that from 0 to 1/2 it produces a negative, but this is still a positive area. So we're going to, we would have to distribute a negative to this f of x right here. Plus, and then from 1/2 to 2, it would just stay as 2x minus 1 dx. Do fundamental theorem of calculus on each one. Well, this would simplify to negative 2x plus 1. So when you take the get the antiderivative from negative 2x plus 1, you get negative x squared plus x, and that's from 0 to 1/2, plus take the antiderivative of 2x minus 1, you get x squared minus x from 1/2 to 2. After you go and do this whole method again, I don't have that much room here because I've got the next example right under here, but just go through the same process as the first example, watch your negative signs, but once you get that, your answer should come out to be 5/2. This last one is dealing with a trig function. So here we have the integral from 0 to pi over 4 of secant squared x dx. First thing you're going to want to do is just, if you can recall, the antiderivative of secant squared x is tangent x. And then we're going from 0 to pi over 4. So it's asking for tangent of pi over 4 minus tangent of 0. And so that's going to equal 1 minus 0. And so your answer is just 1. Guess I could have moved this example down, but oh well. Another topic in 4.4 is the mean value theorem for integrals. Right there. And what it states is that the integral from a to b of f of x dx is the same as f of c times b minus a. So here's just a picture of it. What it's saying is that at some point c within the interval a to b, there's going to be a value such that the rectangle created at that point would equal the actual area under the entire curve from within the interval. So if you take a look here, we've got, we're adding on this section, but we're taking out this section. And so essentially these two cancel each other out, which means that the rest of the area would be equal to all of it, to the would be accurate to the area under the curve. F of c, it's just saying this value right here, and then times b minus a, that's going to give you the value right there. And so it's it's hard that you'll likely see this on the AP test, but it's just a topic. So here's an example for it. So find the value of c guaranteed by the mean value theorem for integrals for f of x equals 9 divided by x to the third on the interval 1 to 3. So it's asking for, so find the value of c. So what we're doing is we're solving for this x value that's within the interval that's going to produce that point on the graph in which if a rectangle was to be drawn there, then it would precisely measure the area underneath the whole curve from A to B. First thing I would do before I start integrating is just rewrite this as f of x equals 9x to the negative third. Now I can do my integration with the fundamental theorem of calculus. So that's going to give me 9x to the negative second divided by negative 2, and that's from 1 to 3. When you use the fundamental theorem of calculus on this, it's going to equal out to 4. And so remember that this fundamental theorem of calculus is equal to the integral from a to b of f of x dx. So essentially, this right here is equal to 4. And so if this is equal to 4, and we have this this whole part right here equal to f of c times b minus a, we can plug this 4 into this side of the equation and then use that to solve for c, which is what we want. So from here we're just going to go 4 equals f of c times b minus a. In this case, b is 3 and a is 1, so it's just going to be 3 minus 1 like that. So now 4 equals f of c times 2. If you divide by 2 on both sides, you get 2 equals f of c. Now, in order to find out what c is, we're going to plug this in for right here. Because essentially, c is just an x value. And so, with some x value, we will get 2. And at the x value that equals 2 is our mean value theorem point. So 2 equals 9 over x to the third, multiply by x to the third on both sides, divide by 2, raise each side to the 1/3 power, and it's approximately 1.65. and that's your C value.